Sponsored by Brilliant. This is not electricity. You can't see electricity, you can only see its effects, such as light, heat, motion, magnetic fields, very expensive bills, and electric arcs. Take this simple circuit with a battery, a switch, a lamp, and a wire connecting them all together. The battery is adding energy to the circuit, and the lamp is removing this, transforming it into light and heat. We can flip the switch to control this. What's happening is tiny particles called electrons are moving through the wire from the battery's negative terminal through the lamp and into the positive terminal. They actually move a very small distance, but I'll explain that in just a moment. Many of us were taught that electricity flows from the positive to the negative. That's because long ago, Benjamin Franklin theorized that electricity was an invisible fluid. He rubbed a glass rod with a cloth, which then gave him a shock. He believed the cloth was adding more of this fluid, making it positive, while the person touching it had less, which made them negative. So he assumed that electricity flowed from positive to negative. Schools then taught this information, many still do, and we call this conventional current. Some years later, Joseph Thomson experimented with a cathode ray tube, a device with two metal plates in a vacuum. When powered, a strange ray appeared, and it oddly travelled from the negative to the positive side. He observed that a magnetic field influenced the ray's direction. He also noticed that when passed between electrically charged plates, it deflected in the electric field between them towards the positive side. As we know, like charges repel and opposites attract. So the beam must be made of tiny particles with a negative charge that moves from negative to the positive. He called these particles an electron, and we call this electron flow. Unfortunately, Benjamin Franklin had guessed incorrectly. The cloth was removing electrons from the glass rod, and they were moving from the person to the rod. The common analogy is that the battery is like a pump, providing the pressure to push the current through the circuit. We measure this electrical pressure in the unit of volts. For example, this battery is rated to provide 1.5 volts, and this one is rated for 9 volts. The water flowing through the pipe is similar to the electrons flowing through the wires. We measure the flow rate in quantity per time, and we measure the current in amperes, or just amps. 1 amp is equal to 1 coulomb per second, which means that if 1 amp was flowing through this wire, then we would have 1 coulomb of charge per second passing this point. An experiment by Robert Millikan calculated the charge of an electron, which is a tiny number. But from that, we can calculate how many electrons are flowing, and we see that 1 amp is equal to around 6.2 quintillion electrons per second. So we just say 1 amp to make it easier. The lamp is adding resistance to the circuit, similar to a section of thin pipe, limiting how much water can flow. We measure the resistance in the unit of ohms. So the voltage is the pushing force, which moves the electrons, and the resistance makes it difficult, so it limits the amount of current which can flow. But we can use Ohm's law to calculate the resistance, voltage, or current in a circuit as long as we know two values. So if we measure the current in this circuit and we know the voltage, then we can easily calculate the resistance. From that, we can calculate how much energy is being consumed. By the way, I did make these handy mugs with all the formulas on, making it quick and easy to use. Links down below if you would like one. So where are these electrons coming from? Well, they are already in the wire, although some do come from the battery. The wire is typically made from copper, which is just a structure of many tiny copper atoms. Atoms are so small that this cubic centimeter of copper contains over 84 sextillion atoms. So this wire contains a lot more. An atom is just a collection of 3 particles, the electron, neutron, and proton. Different elements have different numbers of these particles. These elements are listed in the periodic table, and here we can see copper. I'm going to use the Bohr model to illustrate the atom, but some of you will be familiar with the more accurate quantum mechanics model of an atom. This is very complex and beyond this video, so we're going to use the Bohr model. This shows that the copper atom has 29 protons and 35 neutrons at the center, which forms the nucleus. It also has 29 electrons around the nucleus in different orbital shells. In the outermost valence shell, there is one electron, which is free to move around to other copper atoms. Due to ambient thermal energy, these electrons will naturally move around. They are mobile, and they move randomly in any and all directions. These mobile electrons are bouncing off of atoms and ending up roughly where they started. While some move left, some move right, so the average is 0. The electrons are negatively charged, and the protons are positively charged. Neutrons have no charge. When an electron leaves the atom, there are more protons, so it has a positive charge, and we call this an ion. The copper atoms are all sharing electrons, so inside the wire we have the same number of electrons and protons. Therefore, it is balanced and no charge exists inside the wire. The protons are positively charged and their electric field lines point radially outwards, while electrons are negatively charged and their field lines point radially inwards. The field lines of two electrons or two protons will repel each other, but a proton and an electron will attract. If we connect a plate to each terminal of a battery, we would have a buildup of negative charge on one side and positive charge on the other side. If you imagine that these magnets are electrons and they are creating a neutral charge with their protons, when the battery adds an electron, it squeezes them, so the charge has increased. They only need to move a small amount for that to happen. We know that magnets can interact through their magnetic fields over a long distance without physical contact. The same with electric charges. Their electric field lines reach out across the gap. We can see that by applying a high voltage across these two plates. The grass seeds will align with the electric field, revealing the electric field lines. By the way, these arrows indicate the direction a positive charge would move. In our case, we use electrons, which are negatively charged, so they move in the opposite way of the arrow, which is a little confusing, but just remember it moves from negative to positive. Our battery has a negatively and positively charged end, so it has an electric field. By connecting a wire, we can direct an electric field through the wire, which helps to move the electrons from the negative to the positive terminal. The electrons still move randomly, but the electric field causes them to drift towards the positive terminal. As they move together through the wire, they create a magnetic field around the wire. We can see that using some compasses. We use this to build electromagnets, and it's also used to drive electric motors. So how far do electrons move? Well, let's assume a current of 1 amp is flowing through this wire. We can calculate the drift speed, which is less than 0.1 millimeters per second, which means it would take a very long time to travel this small distance. But when I flip the switch, the light turns on. So how can electrons travel so slowly? If you imagine these are electrons, when we move an electron at one end, its influence travels much further and faster. In the wire, we have an initial pulse of electric and magnetic fields propagating down the wire at close to the speed of light. Then an electric field causes the electrons to drift because of the surface charges, and we'll see that in just a moment. If I take 1 meter of this resistive wire, the resistance gradually increases along the length of the wire. By the way, this is different to standard copper wire. We use it in things like toasters because the large resistance creates heat. Copper wires have almost no resistance. If we applied 10 volts across the ends, the voltage gradually reduces along the wire, but the current is the same at each point. That's because the magnitude of the electric field inside the wires is the same. So something is happening when we connect the wire to the battery. The battery contains a mixture of materials, specifically selected because they produce a chemical reaction which absorbs electrons on one side and ejects electrons on the other side. Imagine that the chemical reaction pulls in an electron and forces it to one end. Each time this happens, the electric field grows and makes it harder for another electron to move across. But the chemical reaction force is so strong that it keeps moving them until the forces become equal, and then it stops. If an electron leaves, the forces are unbalanced, so the chemical reaction forces another electron across to restore and maintain that balance. For me to move these magnets towards each other requires energy. They want to repel. For the chemical reaction to move this electron against the electric field also requires energy. For every coulomb of charge moved, it requires 1.5 joules of energy. That is our voltage, our electromotive force. This is the pressure the battery can provide. Other chemical reactions can provide different voltages. So, due to the chemical reaction, we therefore have a buildup of negatively charged electrons on one side, and the other side has a shortage of electrons, giving us effectively a positive and negative terminal. This charge at the ends of the battery is going to create its own electric field. Remember, our piece of resistive wire has a neutral charge inside because of the balance of protons and electrons. No electric field exists, and so no current flows. But when connected across a battery, the battery pushes electrons into one end and pulls them out of the other. So the buildup of charge at these terminals needs to transition from negative to positive along the length of this resistive wire, which forms a gradient of charge. The charge is on the surface of the wire. We can think of it like a ring. There are regions with higher concentrations near the battery, lower regions elsewhere, and a transition point where it flips from negative to positive. Imagine we took a disk of copper. The protons and mobile electrons are balanced, but if we added some electrons to the center, they repel the other electrons away, and they can only go as far as the surface. The charge at the center remains balanced, so the excess charge must accumulate at the surface. If we remove some electrons from the center, the remaining electrons have more space, and they expose some of the positive charge of the protons. This effectively gives us a positively charged ring. So at the transition point, we have a positive and negatively charged ring, and on the sides, we just have two rings which are both negative or both positive, but one is slightly less charged than the other. Whenever we have a difference in charge, we have an electric field which points from the more positive to the negative. So an electron in this field will be forced towards the less negatively charged region. If you imagine it takes energy to force these repelling charges together, the energy is stored in the field between them. We can use this to move other charges. The gradient of charge creates an electric field around the entire circuit, which forces the electrons to move. The energy is stored in a charge around the wires. This resistive wire is the same diameter and the same material, and the current is the same at each point. So the magnitude of the electric field must also be the same, which is caused by the surface charges. In a normal circuit, the wires have almost no resistance, and they are relatively thick compared to the thin wire of the lamp. The electrons are very easy to move through the copper wire, but it's very hard to move them through the thin lamp filament. So the surface charges mostly accumulate at the battery terminals and either side of the lamp filament, with very little gradient needed along the copper wire. Using a multimeter, we can see nearly the full battery voltage across the lamp, with only a small voltage drop along the wire. If you think about water passing through a hose, when we place our thumb over the end, we reduce the cross-sectional area, so the water flows faster through this part, even though the same quantity of water flows before and after this point. The same must happen with electrons in the filament of the lamp. The electric field is stronger because of the steeper surface charge gradient, and that causes a higher drift velocity. But the same quantity of electrons move, so we have the same current. We can look at the math behind that in my course where I have more time to explain this. Links down below for that if you're interested. But these electrons are going to collide with atoms in the filament and transfer their kinetic energy into the lattice. It's very difficult for the electrons to flow through, so it keeps happening. The electrons slow down, but the electric field keeps forcing them to move, and they collide again and again. With each collision, the filament becomes hotter and hotter, and eventually it becomes so hot that it emits visible light. Now, the circuit typically has a switch to control when current can flow through the lamp. The battery is usually already inserted, and the switch is on the positive side. That means that this section becomes negatively charged, and this section becomes positively charged. So we have an electric field around the wire, but not in the wire, so no current will flow. When the switch closes, some very complex interactions happen within a fraction of a second before the light fully turns on. I'm going to briefly explain what happens. When the switch closes, the charges along the face of the switch will meet and cancel out, leaving just the surface charge rings with strong opposite charges. This creates an electric field which moves an electron. As the electron approaches the positive ring, that ring becomes slightly less positive and the negative ring becomes slightly less negative. Electrons are starting to move, so a magnetic field is developing, and the change in surface charge creates an electric field. The disturbance affects the immediate neighboring sections, so the electric and magnetic fields travel like a wave down the wire in both directions. But other sections of the circuit are unaware of this change at this moment. The electric field reaches out across the gap and influences the surface charges elsewhere in the circuit, creating small disturbance waves and a tiny current here too. As these waves move along the wire, they will hit parts which cause partial reflection waves. These waves interact with other waves, and they help to establish the gradient of surface charges and the electric fields, which stabilizes the circuit, and the light eventually illuminates with a constant current flowing everywhere in the circuit. All of this happens the moment we flip the switch. The electrons move such a small distance that they can't carry the energy from the battery. It's the electric field in the wire that accelerates them to deliver the energy where needed, and this electric field is due to the surface charges along the wire. It can be difficult to understand electrical engineering topics and the math behind them, but our sponsor Brilliant is where you learn by doing. There's so many new courses, but I really enjoyed their new Vectors course. The graphics and interactions just made it so easy to visualize each step, and there was extra help if I needed it. Brilliant has thousands of interactive lessons in math, data analysis, programming, and AI. All the skills you need to become a brilliant engineer. They even have an app for on-the-go learning, making it easy to build your critical thinking skills through problem solving, not memorizing. Each lesson is filled with hands-on problem solving that lets you play with concepts. I think you'll enjoy this too, so you can try everything Brilliant has to offer for free for 30 days. Just visit brilliant.org/The Engineering Mindset, or you can scan the QR code. You'll also get 20% off an annual premium subscription. Do check them out, links down below. Hey, I'd just like to give a huge shout out to our incredible Patreon and channel members. Thank you so much for supporting us. And if you'd like to see your name here, along with priority access to our content and behind the scenes footage, links down below for how to join.